What's up guys, my name is Muhammad Rakib bin Adam and my matrix number is TK23026. Today I want to tell you about battery for electric vehicles. Let's go! First of all, we must know what is EV or an electric vehicle. An electric vehicle is a vehicle that uses one or more electric motors for propulsion. It can be powered by a collector system with electricity from extravehicular sources, or it can be powered autonomously by a battery. The battery is sometimes charged by solar panels or by converting fuel to electricity using fuel cells or a generator. EVs include but are not limited to road and rail vehicles, and broadly can also include electric boat and underwater vessels such as submersibles, and technically also diesel and turboelectric submarines, electric craft, and electric spacecraft. Electric road vehicles include electric passenger cars, electric buses, electric trucks, and personal transporters such as electric buggy, electric tricycles, electric bicycles, and electric motorcycles. Together with other emerging automotive technologies such as autonomous driving, connected vehicle, and shared mobility, EVs form a future vision of transportation called connected, autonomous, shared, and electric mobility. Early electric vehicles first came into existence in the late 19th century, when the second industrial revolution brought forth electrification. Using electricity was among the preferred methods for motor vehicle propulsion, as it provides a level of quietness, comfort, and ease of operation. Ease of operation that could not be achieved by the gasoline engine cars of the time, but range anxiety due to the limited energy storage offered by contemporary battery technologies hindered any mass production of private electric vehicles throughout the 20th century. Internal combustion engines like gasoline and diesel engines were the dominant propulsion mechanism for cars and trucks for about 100 years, but electricity-powered locomotion remained commonplace in other vehicle types such as overhead line-powered mass transit vehicles like electric trains, trams, monorails, and trolley buses, as well as very small, low-speed, short-range battery-powered personal vehicles such as mobility scooter. Hybrid electric vehicles, where electric motors are used as a supplementary propulsion to internal combustion engines, become more widespread in the late 1990s. Plug-in hybrid electric vehicles, where electric motors can be used as the predominant propulsion rather than a supplement, did not see any mass production until the late 20s, and battery electric cars did not become practical option for the consumer market until 2010s. Now we know what is electric vehicle, so we must go to battery electric vehicle. Let's go! Okay, that's it for electric vehicle EV. Now we move on to the next topic is electric vehicle battery. What is electric vehicle battery? An electric vehicle battery, also known as a traction battery, is a rechargeable battery used to power the electric motors of a battery electric vehicle (BEV) or hybrid electric vehicle (HEV). Electric vehicle batteries differ from starting, lightning, and ignition batteries, as they are typically lithium-ion batteries that are designed for high power-to-weight ratio and energy density. Smaller, lighter batteries are desirable because they reduce the weight of the vehicle and therefore improve its performance. Compared to liquid fuels, most current battery technologies have much lower specific energy, and this often impacts the maximum range of all electric vehicles. Unlike earlier battery chemistries, notably nickel-cadmium, Lithium-ion batteries can be discharged and recharged daily and at any state of charge. Other types of rechargeable batteries used in electric vehicles include lead-acid, nickel-cadmium, nickel metal hydride, and others. The battery makes up a significant portion of the cost and environmental impact of an electric vehicle. Growth in the industry has generated interest in securing ethical battery supply chains, which present many challenges and has become an important geopolitical issue. As of December 2019, the cost of electric vehicle batteries has fallen 87% since 2010 on a per kilowatt hour basis. As of 2018, vehicles with over 400 km of all-electric range, such as Tesla Model S, are available. The price of electricity to run an electric vehicle is a small fraction of the cost of fuel for equivalent internal combustion engines, reflecting higher energy efficiency. Now we go to the next one. Let's go! It is about the development of the batteries. After this, we will get to know what types of battery that can be used in EV. Let's go! There are many types of batteries such as lithium-ion battery, nickel-cadmium battery, zinc-carbon battery, cell battery, coin cell battery, nickel metal hydride battery, alkaline battery, and lead-acid battery. We will go through one by one of the type of battery, and we starting with the lead-acid batteries. Flooded lead-acid batteries are the oldest, cheapest, and in the past, most common vehicle batteries available. There are two main types of lead-acid batteries: automobile engine starter batteries and deep cycle batteries. Automobile engine starter batteries are designed to use a small percentage of their capacity to provide high charge rates to start the engine, while deep cycle batteries are used to provide continuous electricity to run electric vehicles like forklift or golf carts. Deep cycle batteries are also used as the auxiliary batteries in recreational vehicles, but they require different multi-stage charging. No lead-acid batteries should be discharged below 50% of its capacity, as it shortens the battery's life. Flooded batteries require inspection of electrolyte levels and occasional replacement of water, which gases away during the normal charging cycle. Previously, most electric vehicles used lead-acid batteries due to their mature technology, high availability, and low cost, with the notable exception of some early BEVs, such as the Detroit Electric, which used a nickel-ion battery. Deep cycle lead batteries are expensive and have a shorter life than the vehicle itself, typically needing replacement every 3 years. Lead-acid batteries in EV application ends up being significant 25 to 50% portion of the final vehicle mass. Like all batteries, they have significantly lower specific energy than petroleum fuels. In this case, 30 to 50 watt-hour per kilogram, while the difference isn't as extreme as it first appears due to the lighter drivetrain in an EV. Even the best batteries tend to lead to higher masses when applied to vehicles with a normal range. The efficiency is 70 to 75% and storage capacity of the current generation of common deep cycle lead-acid batteries decrease with lower temperatures, and diverting power to run a heating coil reduce efficiency and range by up to 40%. Charging and operation of batteries typically results in the emission of hydrogen, oxygen, and sulfur, which are naturally occurring and normally harmless if properly vented. Early city car owners discovered that, if not vented properly, unpleasant sulfur smells would leak into the cabin immediately after charging. Lead-acid batteries powered such early modern EVs as the original version of the EV1. The next one is nickel metal hydride battery. A nickel metal hydride battery is a type of rechargeable battery. The chemical reaction at the positive electrode is similar to that of the nickel cadmium cell, with both using nickel oxide hydroxide. However, the negative electrodes use a hydrogen absorbing alloy instead of cadmium. Nickel metal hydride batteries can have 2 to 3 times the capacity of nickel cadmium batteries of the same size, with significantly higher energy density, although only half of lithium ion batteries. They are typically used as a substitute for similarly shaped non-rechargeable alkaline batteries, as they feature a slightly lower but generally compatible cell voltage and are less prone to leaking. Nickel metal hydride batteries are now considered a relatively mature technology. While less efficient 60 to 70% in charging and discharging than even lead acid, they have a specific energy of 30 to 80 watt per hour kilogram, far higher than lead acid. When used properly, nickel metal hydride batteries can have exceptionally long life, as has been demonstrated in their use in hybrid cars and in the surviving first generation nickel metal hydride Toyota RAV4 EVs that still operate well after 100,000 miles and over a decade of service. Downsides include the poor efficiency, high self-discharge, very finicky charge cycles, and performance in cold weather. GM Ovonic produced the nickel metal hydride battery used in the second generation EV1, and Kobayashi makes a nearly identical battery. 10 1.2 volt 85 ampere per hour nickel metal hydride cells in a series, in contrast with 11 cells for Ovonic battery. This worked well in the EV1. Patent encumbrance has limited the use of these batteries in recent years. When fast charging, it is advisable to charge the nickel metal hydride cells with a smart battery charger to avoid overcharging, which can damage cells. The next one for EV batteries is the sodium nickel chloride. The sodium nickel chloride, or Zebra battery, uses a molten sodium chloroaluminate salt as the electrolyte. A relatively mature technology, the Zebra battery has a specific energy of 120 watt-hour per kilogram. Since the battery must be heated for use, cold weather does not strongly affect its operation except for increasing heating costs. They have been used in several EVs such as the Model commercial vehicle. Zebra batteries can last for a few thousand charge cycles and are non-toxic. The downsides to the Zebra battery include peak power, less than 300 watt per kilogram, and the requirement of having to heat the electrolyte to about 270 degrees Celsius, which wastes some energy, present difficulties in long-term storage of charge, and is potentially a hazard. Molten salt batteries are a class of battery that use molten salt as an electrolyte and offer both a high energy density and a high power density. Traditional non-rechargeable thermal batteries can be stored in their solid state at room temperature for long periods of time before being activated by heating. Rechargeable liquid metal batteries are used for industrial power backup, special electric vehicle, and for grid energy storage, to balance out intermittent renewable power sources such as solar panel and wind turbine. The next one is lithium-ion battery. Lithium-ion and the mechanistically similar lithium polymer batteries were initially developed and commercialized for use in laptops and consumer electronics. With their high energy density and long life cycle, they have become the leading battery type for use in EVs. The first commercialized lithium-ion chemistry was a lithium cobalt oxide cathode and a graphite anode, first demonstrated by N. Gottschall in 1979 and by John Goodenough and Akira Yoshino shortly thereafter. The downside of traditional lithium-ion batteries include insensitivity to temperature, low temperature, power performance, and performance degradation with age. Due to the volatility of organic electrolytes, the presence of highly oxidized metal oxides, and the thermal instability of the anode layer, traditional lithium-ion battery pose a fire safety risk if punctured or charged improperly. These early cells did not accept or supply charge when extremely cold, and so heaters can be necessary in some climates to warm them. The maturity of this technology is moderate. The Tesla Roadster and other car produced by the company use a modified form of a traditional lithium-ion laptop battery cell. Recent EVs are using new variation on lithium-ion chemistry that sacrifice specific energy and specific power to provide fire resistance, environmental friendliness, rapid charging as quickly as a few minutes, and longer lifespan. These variants, phosphate, titanate, spinels, and etc., have been shown to have a much longer lifetime, with A123 types using lithium iron phosphate lasting at least more than 10 years and more than 7,000 charge or discharge cycle, and LG Chem expecting their lithium manganese spinel batteries to last up to 40 years. Much work is being done on lithium-ion batteries in the lab. Lithium vanadium oxide has already made its way into the Subaru prototype G4e, doubling energy density. Silicon nanowires, silicon nanoparticles, and thin nanoparticles promise several times the energy density in the anode, while composite and superlattice cathodes also promise significant density improvements. New data has shown that exposure to heat and the use of fast charging promote the degradation of lead-ion batteries more than age and actual use, and that the average electric vehicle battery will retain 90% of its initial capacity after 6 years and 6 months of service. For example, the battery in a Nissan Leaf will degrade twice as fast as the battery in a Tesla, because the Leaf does not have an active cooling system for its battery. The next one is nickel-cadmium battery. The nickel-cadmium battery, NICD battery or NiCad battery, is a type of rechargeable battery using nickel oxide hydroxide and metallic cadmium as electrodes. The abbreviation NICD is derived from the chemical symbols of nickel Ni and cadmium Cd. The abbreviation NiCad is a registered trademark of SAFT Corporation, although this brand name is commonly used to describe all NICD battery. Wet cell nickel-cadmium batteries were invented in 1899. A NiCad battery has a terminal voltage during discharge of around 1.2 volts, which decreases little until nearly the end of discharge. The maximum electromotive force offered by NiCad cell is 1.3 volt. NiCad batteries are made in a wide range of size and capacities, from portable cell types interchangeable with carbon zinc dry cells to large ventilated cells used for standby power and motive power. Compared with other types of rechargeable cells, they offer good cycle life and performance at low temperature with a fair capacity, but their significant advantage is the ability to deliver practically their full rated capacity at high discharge rate. However, the materials are more costly than that of the lead-acid battery, and the cells have high self-discharge rates. Steel NiCad cells were at one time widely used in portable power tools, photography equipment, flashlights, emergency lights, hobby RC, and portable electronic devices. The superior capacity of nickel metal hydride batteries and recent lower cost has largely supplanted NiCad use. Further, The environmental impact of the disposal of the toxic metal cadmium has contributed considerably to the reduction in their use. Within European Union, nickel batteries can now only be supplied for replacement purpose or for certain types of new equipment such as medical device. Larger ventilated wet cell nickel batteries are used in emergency light, standby power, and uninterruptible power supplies and other applications. Nickel cells have a nominal cell potential of 1.2 volts. This is lower than the 1.5 volt of alkaline and zinc carbon primary cells, and consequently they are not appropriate as a replacement in all applications. However, the 1.5 volt of a primary alkaline cell refers to its initial, rather than average, voltage. Unlike alkaline and zinc carbon primary cells, a nickel cell's terminal voltage only charges a little as it discharges. Because many electronic devices are designed to work with primary cells that may discharge to as low as 0.9 to 1.0 per cell, the relatively steady 1.2 volt of a nickel cell is enough to allow operation. Some would consider the near constant voltage a drawback as it makes it difficult to detect when the battery charge is low. Nickel batteries used to replace 9 volt batteries usually only have 6 cells for a terminal voltage of 7.2 volts, while most pocket radios will operate satisfactorily at this voltage. Some manufacturers such as Varta made 8.4 volt batteries with 7 cells for more critical application. Nickel batteries may suffer from a memory effect if they are discharged and recharged to the same state of charge 100 times. The apparent symptom is that the battery remembers the point in its discharge cycle where recharging began, and during subsequent use suffer a sudden drop in voltage at that point, as if the battery had been discharged. The capacity of the battery is not actually reduced substantially. Some electronics designed to be powered by nickel batteries are able to withstand this reduced voltage long enough for the voltage to return to normal. However, if the device is unable to operate through this period of decreased voltage, it will be unable to get enough energy out of the battery, and for all practical purposes, the battery appears dead earlier than normal. There is evidence that the memory effect story originated from orbiting satellites, where they were similarly charging and discharging with every orbit around the Earth over a period of several years. After this time, it was found that the capacities of the batteries had declined significantly, but were still fit for use. It is unlikely that this precise repetitive charging, for example, 1000 charge or discharge with less than 2% variability, could ever be reproduced by individuals using electrical goods. The original paper describing the memory effect was written by GE scientists at their battery business department in Gainesville, Florida, and later retracted by them, but the damage was done. The battery survived thousands of charge or discharge cycles. Also, it is possible to lower the memory effect by discharging the battery completely about once a month. This way, apparently, the battery does not remember the point in its discharge cycle. An effect with similar symptom to the memory effect is the so-called voltage depression or lazy battery effect. This results from repeated overcharging. The symptom is that the battery appears to be fully charged but discharged quickly after only a brief period of operation. In rare cases, much of the lost capacity can be recovered by a few deep discharge cycles, a function often provided by automatic battery chargers. However, this process may reduce the shelf life of the battery. If treated well, a nickel battery can last for 1000 cycles or more before its capacity drops below half its original capacity. Many home chargers claim to be smart chargers which will shut down and not damage the battery, but this seems to be a common problem. The next one is zinc carbon battery. A zinc-carbon battery or carbon-zinc battery in US English is a dry cell primary battery that provides direct electric current from the electrochemical reaction between zinc and manganese dioxide in the presence of an ammonium chloride electrolyte. It produces a voltage of about 1.5 volts between the zinc anode, which is typically constructed as a cylindrical container for the battery cell, and a carbon rod surrounded by a compound with a higher standard electrode potential, known as the cathode, that collects the current from the manganese dioxide electrode. The name zinc carbon is slightly misleading as it implies that carbon is acting as the oxidizing agent rather than the manganese dioxide. General purpose batteries may use an acidic aqueous phase of ammonium chloride as electrolyte with some zinc chloride solution on a paper separator to act as what is known as a salt bridge. Heavy-duty type used as the base primarily composed of zinc chloride. Zinc carbon batteries were the first commercial dry batteries developed from the technology of the wet Leclanche cell. They made flashlight and other portable devices possible because the battery provided a higher energy density at a lower cost than previously available cells. They are still useful in low drain or intermittent use devices such as remote controls, flashlights, clocks, or transistor radios. Zinc carbon dry cells are single-use primary cells. Zinc carbon batteries today have been mostly replaced by the more efficient and safe alkaline batteries. Manufacturers recommend storage of zinc carbon batteries at room temperature. Storage at higher temperature reduces their expected service life. Zinc carbon batteries may be frozen without damage. Manufacturers recommend that they be returned to normal room temperature before use, and that condensation on the battery jacket must be avoided. By the end of the 20th century, the storage life of zinc carbon cells had improved fourfold over expected life in 1910. Zinc carbon cells have a short shelf life. As the zinc is attacked by ammonium chloride, the zinc container becomes thinner as the cell is used, because zinc metal is oxidized to zinc ions. When the zinc case thins enough, zinc chloride begins to leak out of the battery. The old dry cell is not leak-proof and becomes very sticky as the paste leaks through the hole in the zinc case. The zinc casing in the dry cell gets thinner even when the cell is not being used, because the ammonium chloride inside the battery reacts with the zinc and inside out from with a carbon cup and zinc vanes on the interior, while more leak resistance has not been manufactured since the 1960s. After this, we will tell about coin cell battery. A button cell, watch battery or coin battery is a small single cell battery shaped as a squat cylinder, typically 5 to 25 mm in diameter and 1 to 6 mm high, resembling a button. Stainless steel usually forms the bottom body and positive terminal of the cell. Insulated from it, the metallic top cap forms the negative terminal. Button cells are used to power small portable electronics devices such as wristwatch and pocket calculators. Wider variants are usually called coin cell. Devices using button cells are usually designed around a cell giving a long service life, typically well over a year in continuous use in a wristwatch. Most button cells have low self-discharge, holding their charge for a long time if not used. Relatively high-power devices such as hearing aids may use a zinc air battery, which has a much higher capacity for a given size, but dries out after a few weeks even if not used. Button cells are single cells, usually disposable primary cells. Common anode material are zinc or lithium. Common cathode material are manganese dioxide, silver oxide, carbon monofluoride, cupric oxide or oxygen from the air. Mercury oxide button cells were formerly common, but are no longer available due to the toxicity and environmental effect of mercury. Button cells are dangerous for small children as when swallowed they can cause severe internal burns and significant injury or death. Duracell has attempted to mitigate this by adding a bitter coating to their batteries. In addition to disposable, single-use button cells, rechargeable batteries in many of the same size are available, with lower capacity than disposable cells. Disposable and rechargeable batteries are manufactured to fit into a holder or with solder tags for permanent connection. In equipment with a battery holder, disposable or rechargeable batteries may be used if the voltage is compatible. A typical use for a small rechargeable battery in coin or other format is to back up the settings of equipment which is normally permanently mains powered in the case of power failure. For example, many central heating controllers store operations times and similar information in volatile memory loss in the case of power failure. It is usual for such system to include a backup battery, either a disposable in a holder or a solder in rechargeable. Rechargeable NiCad button cells were often component of the backup battery of older computers. Non-rechargeable lithium button cells with a lifetime of several years are used in later equipment. Rechargeable batteries typically have the same dimension base numeric code with different letters. The CR2032 is a disposable battery, while ML2032, VL2032 and LIR2032 are rechargeable that fit in the same holder if not fitted with solder tags. It is mechanically possible, though hazardous, to fit a disposable battery in a holder intended for a rechargeable battery. Holders are fitted in parts of equipment only accessible by service personnel in such cases. The next one is seal battery. A valve-regulated lead acid (VRLA) battery, commonly known as a seal lead acid (SLA) battery, is a type of lead acid battery characterized by a limited amount of electrolyte absorbed in a plate separator or formed into a gel. Proportioning of the negative and positive plates so that oxygen recombination is facilitated within the cell, and the presence of a relief valve that retains the battery contents independent of the position of the cells. There are two primary types of VRLA batteries: absorbent glass mat AGM and gel cell gel battery. Gel cell adds silica dust to the electrolyte, forming a thick putty-like gel. AGM or absorbent glass mat batteries feature fiberglass mesh between the battery plates which serve to contain the electrolyte and separate the plates. Both types of VRLA batteries offer advantage and disadvantage compared to flooded vented lead acid VLA batteries or each other. Due to their construction, the gel cell and AGM types of VRLA can be mounted in any orientation and do not require constant maintenance. The term maintenance-free is a misnomer as VRLA batteries still require cleaning and regular functional testing. They are widely used in large portable electrical devices, off-grid power system and similar roles where large amounts of storage are needed at a lower cost than other low-maintenance technologies like lithium-ion. Lead acid cells consist of two plates of lead, which serve as electrodes suspended in an electrolyte consisting of diluted sulfuric acid. VRLA cells have the same chemistry except the electrolyte is immobilized. In AGM, this is accomplished with a fiberglass mat. In gel batteries or gel cells, the electrolyte is in the form of a paste-like gel created by adding silica and other gelling agents to the electrolytes. When a cell discharges, the lead and diluted acid undergo a chemical reaction that produces lead sulfate and water. When a cell subsequently charged, the lead sulfate and water are turned back into lead and acid. In all lead acid battery line, charging current must be adjusted to match the ability of the battery to absorb the energy. If the charging current is too great, electrolysis will occur, decomposing water into hydrogen and oxygen. In addition to the intended conversion of lead sulfate and water into lead dioxide, lead and sulfuric acid, the reverse of the discharge process. If these gases are allowed to escape, as in a conventional flooded cell, the battery will need to have water or electrolyte added from time to time. In contrast, VRLA batteries retain generated gas within the battery as long as the pressure remains within safe levels. Under normal operating conditions, the gases can then combine within the battery itself, sometimes with the help of a catalyst, and no additional electrolyte is needed. However, if the pressure exceeds safety limits, safety valves open to allow the excess gases to escape, and in doing so regulate the pressure back to safe level. Now we will go through detail about lithium-ion batteries. A lithium-ion or Li-ion battery is a type of rechargeable battery which uses the reversible intercalation of Li plus ions into electronically conducting solid to store energy. In comparison with other rechargeable batteries, Li-ion batteries are characterized by a higher specific energy, higher energy density, higher energy efficiency, longer cycle life, and longer calendar life. Also noteworthy is a dramatic improvement in lithium-ion battery properties after their first market introduction in 1991. Within the next 30 years, their volumetric energy density increased threefold, which their cost dropped tenfold. The invention and commercialization of Li-ion batteries is considered as having one of the largest societal impact in human history among all technologies, as we recognized by 2019 Nobel Prize in Chemistry. More specifically, Li-ion batteries enable portable consumer electronics, laptop computers, cellular phone, and electric cars, or what has been called e-mobility revolution. It also seen significant use for grid-scale energy storage as well as military and aerospace application. Although many thousands of different materials have been investigated for use in lithium-ion batteries, the usable chemistry space for this technology that made into commercial application is extremely small. All commercial Li-ion cells use intercalation compounds as active materials. The first one is the anode or negative electrode is usually graphite, although silicon has been often mixed with graphite in commercial cells since 2015. 2. The solvent in commercial Li-ion batteries comprise organic carbonates such as ethylene carbonate and dimethyl carbonate that form solid electrolyte interface on the anode, which allow for Li plus ion transport but not for electron transfer. 3. In addition to carbonate solvent, the battery electrolyte comprises a lithium salt. Lithium hexafluorophosphate is most commonly used because it passivates the positive aluminum current collector. 4. There is more diversity among positive electroactive material, cathodes. They are selected from a group comprising layered LiCOO2 and LiNiO2, spinel LiMn2O4, olivine life PO4, and their combinations derivative. Many other post-hot materials have been studied, but they all suffer either from a high cost, poor durability, or to high voltage incompatible with non-electrolytes. 5. The negative current collector is usually made of copper and it uses a spot well nickel current collector. 6. The positive current collector is usually made of aluminum and it uses an ultrasonically well titanium tap. Lithium-ion cells can be manufactured to optimize energy or power density. Handheld electronics mostly use lithium polymer batteries, a lithium cobalt oxide cathode material, and a graphite anode, which together offer high energy density. Lithium iron phosphate, lithium manganese oxide, spinel, or lithium-rich layered material, and lithium nickel manganese cobalt oxide may offer longer life and a higher discharge rate. NMC and its derivatives are widely used in the electrification of transport, one of the main technologies for reducing greenhouse gas emission from vehicles. M. Stanley Whittingham conceived intercalation electrodes in 1970s and created the first rechargeable lithium-ion battery based on a titanium disulfide anode and a lithium aluminate cathode, although it suffered from safety problems and was never commercialized. John Goodenouth expanded on this work in 1980 by using lithium cobalt oxide as a cathode. The first prototype of the modern lithium-ion battery, which used a carbonaceous anode rather than lithium metal, was developed by Akira Yoshino in 1985, which was commercialized by a Sony and Asahi Kasei team led by Yoshino Nishi in 1991. M. Stanley Whittingham, John Goodenough, and Akira Yoshino were awarded the 2019 Nobel Prize in Chemistry for their contribution to the development of lithium-ion batteries. Lithium-ion batteries can be safety hazard if not properly engineered and manufactured, because cells have flammable electrolytes, and if damaged or incorrectly charged, can lead to explosion and fires. Much progress has been made in the development and manufacturing of safe lithium-ion batteries. Lithium-ion all-state batteries are being developed to eliminate the flammable electrolyte. Improperly recycled battery can create toxic waste, especially from toxic metals, and are at risk of fire. Moreover, both lithium and other key strategic minerals used in battery have significant issues at extraction, with lithium being water-intensive in often arid regions, and other minerals often being conflict minerals such as cobalt. Both environmental issues have encouraged some researchers to improve mineral efficiency and alternatives such as ion batteries. Research area for lithium-ion batteries include extending lifetime, increasing energy density, improving safety, reducing cost, and increasing charging speed. Among others, research has been underway in the area of non-flammable electrolyte as a pathway to increase safety based on the flammability and volatility of the organic solvent used in a typical electrolyte. Strategies include aqueous lithium-ion batteries, ceramic solid electrolytes, polymer electrolytes, ionic liquids, and heavily fluorinized system. For the performance of lithium-ion batteries, lithium-ion batteries can have a variety of positive and negative electrodes material. The energy density and voltage vary accordingly. The open circuit voltage is higher than in aqueous batteries. Internal resistance increases with both cycling and age, although this depends strongly on the voltage and temperature the batteries are stored at. Rising internal resistance causes all the voltage at the terminals to drop under load, which reduces the maximum current draw. Eventually, increasing resistance will leave the battery in a state such that it can no longer support the normal discharge current request of it without unacceptable voltage drop of overheating. Batteries with a lithium-ion phosphate, positive, and graphite negative electrodes have a normal open circuit voltage of 3.2 volt and a typical charging voltage of 3.6 volt. Lithium nickel manganese cobalt NMC oxide positive with graphite negative have a 3.7 volt nominal voltage with a 4.2 volt maximum while charging. The charging procedure is performed at constant voltage with current limiting circuitry. Charging is constant currently until its voltage of 4.2 volt is reached in the cell, and continuing with a constant voltage applied until the current drops close to zero. Typically, the charging is terminated at 3% of the initial charge current. In the past, lithium-ion batteries could not be fast charged and needed at least 2 hours to fully charge. Current generation cells can be fully charged in 45 minutes or less. In 2015, researchers demonstrated a small 600 mAh capacity battery charged at 68% capacity in 2 minutes and a 3000 mAh battery charged to 48% capacity in 5 minutes. The latter battery has an energy density of 620 watt-hour per liter. The device employed heteroatoms bound to graphite molecules in the anode. Performance of manufactured batteries has improved over time. For example, from 1991 to 2005, the energy capacity per price of lithium-ion batteries improved more than tenfold, from 0.3 watt-hour per dollar to over 3 watt per hour per dollar. In the period from 2000 to 2017, progress has averaged 7.5 annually. Overall, between 1991 and 2018, price for all types of lithium-ion cells in dollar per kilowatt fell approximately 97%. Over the same time period, energy density more than tripled. Efforts to increase energy density contribute significantly to cost reduction. Differently sized cells with similar chemistries can also have different energy densities. The 21,700 cell has 50% more energy than the 18,650 cells, and the bigger size reduces heat transfer to its surrounding. The lifespan of a lithium-ion battery is typically defined as the number of full charge-discharge cycles to reach failure threshold in terms of capacity loss or impedance rise. Manufacturers' datasheet typically use the word cycle life to specify lifespan in terms of the number of cycles to reach 80% of the rated battery capacity. Simply, storing lithium-ion batteries in the charged state also reduces their capacity and increase the cell resistance. Calendar life is used to represent the whole life cycle of battery, involving both the cycle and active storage operation. Battery cycle life is affected by many different stress factors including temperature, discharge current, charge current, and state of charge change. Batteries are not fully charged and discharged in real applications such as smartphones, laptops, and electric cars, and hence defining battery life via full discharge cycle can be misleading. To avoid this confusion, researchers sometimes use cumulative discharge, defined as the total amount of charge delivered by the battery during its entire life or equivalent full cycle, which represents the summation of the partial cycle as fraction of a full charge-discharge cycle. Battery degradation during storage is affected by temperature and battery state of charge, and a combination of full charge and high temperature, usually over 50 degrees Celsius, can result in sharp capacity drop and gas generation. Multiplying the battery cumulative discharge by the rated nominal voltage gives the total energy delivered over the life of the battery. From this one, can calculate the cost per kilowatt hour of the energy. Over the lifespan, batteries degrade gradually, leading to reduced capacity and in some cases lower operating cell voltage due to a variety of chemical and mechanical changes to the electrode. Several degradation processes occur in lithium-ion batteries, some during cycling, some during storage, and some all the time. Degradation is strongly temperature dependent. Degradation at room temperature is minimal but increased for batteries stored or used in a high temperature or low temperature environment. High charge level also hasten capacity loss. In a study, scientists provide 3D imaging and model analysis to reveal main cause, mechanics, and potential mitigations of the problematic degradation of the batteries over charge cycle. They found particle cracking increase and contact loss between particle and carbon binder domain are observed to correlate with the cell degradation and indicates that the reaction heterogeneity within the thick cathode caused by the unbalanced electron conduction is the main cause of the battery degradation over cycling. Now we will go through to the mineral in a battery. Inside practically every electric vehicle is a lithium-ion battery that depends on several key minerals that help power it. Some minerals make up intricate parts within the cell to ensure the flow of electrical current. Others protect it from accidental damage on the outside. The cells in the average battery with a 60 kWh capacity, the same size that used in Chevy Bolt, contain roughly 185 kilograms of minerals. This figure excludes materials in the electrolyte, binder, separator, and battery pack casing. The cathode contains the widest variety of mineral and is arguably the most important and expensive component of the battery. The composition of the cathode is a major determinant in the performance of the battery, with each mineral offering a unique benefit. For example, NMC batteries, which accounted for 70% of battery used in EVs in 2020, excluding China, have a cathode composed of nickel, manganese, and cobalt along with lithium. The higher nickel content in these batteries tends to increase their energy density or the amount of energy stored per unit of volume. Increasing the driving range of the EV, cobalt and manganese often act as stabilizer in NMC batteries, improving their safety. Altogether, materials in the cathode account for 31.3% of the mineral weight in the average battery produced in 2020. This figure doesn't include aluminium, which is used in nickel, cobalt, aluminum, and Ca cathode chemistries, but is also used elsewhere in the battery for casing and current collector. Meanwhile, graphite has been the go-to material for anodes due to its relatively low cost, abundance, and long cycle life. Since the entire anode is made up of graphite, it is the single largest mineral component of the battery. Other material include steel in the casing that protects the cell from external damage, along with copper used as the current collector for the anode. With consumer looking for higher range EVs that do not need frequent recharging, nickel-rich cathodes have become commonplace. In fact, nickel-based chemistries accounted for 80% of the battery capacity deployed in new plug-in EVs in 2021. Lithium iron phosphate batteries do not use any nickel and typically offer lower energy densities at better value. Unlike nickel-based batteries that use lithium hydroxide compounds in the cathode, LFP batteries use lithium carbonate, which is a cheaper alternative. Tesla recently joined the several Chinese automakers in using LFP cathode for standard range car, driving the price of lithium carbonate to record highs. The EV battery market is still in its early hour. With plenty of growth on the horizon, battery chemistries are constantly evolving, and as automaker comes up with new models with different characteristics, it will be interesting to see which new cathode comes around the block. Thanks for giving me a cooperation to listen to my presentation. Thank you.